or you see it in high electric high tension electric towers, and several things you see such kind of things. And mostly in for mechanical people, you see it in the shop floor, where if you want to have heavy weights to be transported within the floor, you use gantry girders, and these gantry girders would be inherently supported through the so these are the prevalent things. So for example, I give one such example is some kind of warrant dress. So this is one such example. So what we assumed here, the main assumption in the trusses are, they are the members of the truss are axially loaded members, and the joints are pin jointed. That means all the joints cannot resist movement, so they are free to rotate. Free to rotate at the joints are also known as joints not resist. So we don't take any bending into the consideration, but we know that all the members are made up of material, and hence they have some weight. So by assuming this, you may feel like there is certain big mistake you are, or a big approximation you are making. But nevertheless, I will show how the weight of the given structure can be considered at a later point of time when you are computing the loadings. Okay, but at this point of time, we assume that the members are weightless, so no bending effects are present. Okay, so with this as a structure, so each member, any given member, is a bar element, or also called as link element. Okay, link element is the element which has only axial deformations, or axial degrees of freedom are only active. Axial degree of freedom are only active. We have 2D link element and 3D link element. 2D link elements are also known as plane elements, plane link elements, and these are called space. More or less the formulation is same, but for the given course, I will restrict myself to the plane elements. So I will try to repeat it in a more physical sense in today's class in a slower pace. Okay, so for that, let me take a structure and something like this. let the slope of this is given by 3 by 4. The length of this, let's take it as 4 meters. This one has 3 meters. So obviously the 3 square plus 4 square right angle triangle will have 5 meters in length. And let's have a point load P acting at this end. So let's, each joint is a pin joint. So these things are free to rotate about the node 1, node 2, node 3. So the element that is opposite to the node 1, I call it as element 1. The element that is opposite to the node 2, I call it as element 2. The element that is opposite, I call it as node 3, element 3. Okay, let's have this kind of a thing. So now, since this is there, I just want to find out this. Let's say this is theta, or so let me write cos theta, which I simply write it as C, is equals to, this length is 3 meters, this is 5 meters, so it is 3 by 5. I also call it as 0.6. Similarly, sin theta is equals to S, that is equals to 4 by 5, that is equals to 0.8, because this is 4 and this is 5. Now we want to a bar element, but with a more intuitive manner, I want to get it in the real, in a more physical sense. So in order to do that, what I will ask you guys is to consider this truss again. This is element 1, this is element 2, this is element 3. Now I want to displace this node 1. These are the node 1, this is node 2, this is node 3. This node by 1 mm or by unit 1, let's say. Anyway, let's see the degrees of freedom for everything. This is u1, v1, u2, v2, u3, v3. So horizontal is x distance, vertical is y. The displacements, these are called u in the x direction, and in the y direction the displacements are called v. So at this place, v1 displacement, if I displace in such, okay. So let us take that into the consideration, and this is the nomenclature. So what I will do is I'll take the same truss again, and displace the node 1 by unit distance. Then my members will be something like this. This is the member 1. The member 2 would become something. And member 3 remains same. Okay, this would be the thing. So now in order to sustain this displacement, which is u1 is equals to 1, to keep the structure in this position, I need to have some forces acting on it to keep it under equilibrium. So I would try to compute this forces. Let's come back to here for a bar. So if you have a bar, you are applying a force F. The change in the displacement U because of the force acting this would be which we might have studied in previous classes, right? So, or you can easily derive it because um, it's pretty simple. You have your sigma is equal E is equals to A times sigma. Sorry, your force is equals to A times sigma, that is equals to A E epsilon, but epsilon is equals to du by dx. Okay, for the total thing you can write your this thing approximate as u by L, so that you can write it as for the entire structure AE. Your strain is delta U by original length L. So this is uh, infinite similar strain decimal. This is infinite similar seminal strain as the average strain definition. So by making use of that definition, so we can write, you multiply this will give you F and as F by the stiffness K is defined as F by U. So I know my F is F. The definition of U is given by this one. So I substitute this one as FL by AE from the above. That will give me my definition of stiffness is equals to AE by L. So the stiffness of a bar is determined as AE by L. Okay, so where L is the length of the bar, A is the cross section, E is the material Young's modulus. So similarly, each one has A, it has its own E, and we know its length. Sorry, this is the element 1. Yes. So similarly, it has A3, E3 has its cross sectional area and its Young's modulus, A2 and E2. And correspondingly, we know this length is L1, this is L3, and that is L2. So I can as well as define as the stiffness K1 as A1 E1 by L1, A2 as A2 E2 by L2, and K3 as A3 E3 by its L3. So that is stiffness for each member can be defined as with the corresponding case. So the stiffness of each members, now I denote it as K1, K2 and K3 correspondingly. Now let's come back here. Now when I displace this one with a unit thing, the corresponding force, so that means if my U is 1, if U is 1, then the corresponding force on the structure should be equal to its stiffness. So I know the corresponding stiffness for this one is K3, K2, K1. But when I displace it, this one by unit distance, the force developed in this direction would be, so I'll equal third member is equal to K3, and to kind of to keep it in equilibrium, I need to act, we need to provide another force in the opposite direction at the other end so that the forces are under equilibrium. So this is what happens to the second element. Let's look at the second element. So when we are looking at the second element is displaced by this amount. Let's assume that this angle and this angle are, you can assume that your theta and your theta dash is more or less as theta, because these deformations in the real structures are very small, and they are very small, the difference between theta and theta dash would be negligible. So in that as a scenario, I will assume it. And now I want to know, because this member gets only deformed for the uh, displacements that are only along the axial direction of this member, not in this direction. So split this unit, whatever is the displacement, into the displacement that is along the structure and one is perpendicular to the structure. So let me show it separately. So now if I take this as, and I have displaced it by unit distance, I want to split this unit distance into a component that is parallel to the things, a component that is perpendicular to the thing. So anyway, that the component that is perpendicular for this inclined member doesn't give any deformation, so we are not worried about it. So what we will take is, we'll take this force, which is u1 is equals to 1, and we'll find out what is the component that is there in this. Since this angle theta is this one, so this is also theta, because this is theta, that is also theta. This becomes the cosine component and this will become sine component. So this is c times u1, that is equals to, our c is in our case is defined as 0.6. So displacement along the member is 0.6. The displacement perpendicular is 0.8. The perpendicular thing doesn't give us any deformation, so I'm not worried about 0.8. But this fellow, because I have a force, now the force on the second member is 0.6. Okay, so, or sorry, the displacement, the displacement K2 is equals to F2 by U2. So, but our F I don't know, but U2 in this case is 0.6. The force acting on this element will be given as 0.6 times F2. So, sorry, 0.6 times K2. So a force of a force of a force of 1 k along this thing. So the horizontal, and that is along the vertical direction. K2 6 times another 0.6, 0.36 K1, and this will become 0.48, sorry, K2 and 0.6 into 0.8, because this is sine theta, this will become this one. So that means for the bar 1, let me rewrite it. For the bar 1, element 1, for a unit displacement K3. While for the, this is for the third element. For the second element, the forces were to keep it under the deformed configuration. This is C into S into K2. This is C into K2, that is equals to 0.36 K2 and 0.48 K2. But the same amount of force has to be acting in the other place, 0.48 K2, so that the things are under the equilibrium, 0.36 K2. Right? So with this, we are ready that for a unit displacement. Now let's come to the first element. The first one is unaffected. For this displacement, this is fortunately unaffected. So there are no forces on the first element because of unit displacement change in the node 1. Okay. So now let's write for a deformation of, so what is the deformation I have given? The deformation I have given, this, my deformation what I have given is this one as 1, this one as 0, this one as 0, this one as 0, this one as 0, this one as 0. This is the displacement I have given. To sustain this, to sustain this, I need to have these forces that are acting at the nodes. Let me list it out. The forces, I call the forces as the forces on these members. Let me call it as P1, Q1, P2, Q2, P3, Q3. So I need a force capital Q, Q1, P2, Q2, P3, Q3. So the forces in this case, let us count. So in the node 3, the force is here, it is K3. So, sorry, at the node, this is the node 1. Let us see again. This is the node 1. This is node 1. This is node 2. This is node 1. This is node 3. So at node 1, the force coming from the third element is K3. Similarly, at the node 1, the force coming from the second element is plus 0.36 K2. Similarly, if I count K, the Q, this is minus 0.48 K2 is Q1, 2, the node which is in the opposite direction, not in the positive direction, so it is minus K3. Okay, next, if I count the Q2 which is in this direction, there is nothing, so it is 0. So Q2 is 0. Now come to the third. Here P3 is in the minus direction, so it is minus 0.36 K2, and Q3 is plus 0.48 K2. So my P1 is this one, Q1 is this one, P2 is this one, Q2 is this one. And I add all these forces, you can observe that the sum will be equal to 0. So this is minus 0.48, this is plus 48, so this is cancelled. Minus 0.36 plus 0.36 K2, these two are cancelled. K3 minus K3. So why it is cancelled? Because the system is under self-equilibrium. So the number of positive forces has to be balanced with the at the node 1 along U1 direction. These are the forces required. So I name this one as Q1. That means Q1 is defined as forces required to sustain the displacement of U1 is equals to 1 and all other degrees of freedom equal to 0. That means only my U1 is 1 and all other things are 0. If this is the deformation, then the forces acting at all the nodes would be this value. Okay, now I would also go ahead and I will simply show it quickly and you can go ahead and practice yourself for the rest of the things. So now let me take the structure. Now I would displace this structure. I will displace this structure by this is V1 is equals to 1. So the for this given structure. So again for this deformation, which is 0, 1, 0, 0, 0, 0. Now given displacement, only y displacement at the node 1 by unit distance, and all other things remains as it is. The nodal displacement remains 0. This is the thing. The force field one has to require can be shown would be, but you can compute it yourself. Anyway, I will explain it quickly without rederiving everything. Now, since this is perpendicular to this element, this is an axial member, so the V will not have any stiffness changes or the forces acting in this member. So this is unchanged. So there are no forces in this third element. Now let us look at the first element. The first element is both the nodes are not moved. So even there are no forces because of a unit displacement at this place in this. So there are no forces in this, there are no forces in that. Now let us look at only this guy. Now you have this one which is unit distance. Now this unit distance, let me again elaborate it for one more time. You have a unit displacement in this has to be decomposed into one along the beam and one along the bar and one is perpendicular to the bar. So since this angle is theta, so this angle is 90 minus theta. So since this is 1, the displacement here would be sine of 1. So this is, if this is V1, this would be sine of V1, the displacement of within the structure, and the displacement that is perpendicular to the structure is V1. Anyway, this will not give any change, causes no change in stiffness, so I'm not worried about it. But since this is axial member, it is compressed by S time V1, so that will give me a force field which is equals to S V1 times K2. This is the force acting on the element 2. So this force, because of this displacement, the force acting is equals to K2 times SV1. So this is my force. The same amount of force would be acting in this direction and in this direction. Now I need to decompose this into the horizontal direction and into the vertical direction. Similarly, the horizontal direction and the vertical direction. So again, I know that this angle is theta. So if this angle is theta, then my horizontal direction would give me point or CS V1 K2, and this one become the force in this direction is S into S V1 K2. So this is nothing but 0.64 K2 for V1 is equals to 1, and this will become 0.48 K2. the same amount of things will be acting in the opposite end. So this will become 0.48 K2. This is 0.64 K2. So now because of the displacement, because of this displacement, the force field in the structure is P1, Q1, P2, Q2, P3, Q3. So let us see what are the P1s. So at this node 1, the forces of minus 0.48 K2 is acting in the negative direction. So this is minus 0.48 K2. Next, at this place, the Q1, this is 0.64 in the positive direction. 0.64 K2. Now at the node 2, which is at this end, there are no forces, so it is both are 0. Now this is, since we know this is node 1 and node 3, node 2 is here, this is unaffected, so there are no forces. Now the 3, you have P3 is equals to 0.48 K2 in the positive direction, and Q3 is equals to minus K2. Okay, so that means to sustain this displacement, the forces that are required you to keep on the structure would be, or the forces that are developed in the structure in response to this displacement field is this set of forces. Okay, so which I call it as capital Q2. Okay, this is capital Q2. So similarly, what I do is I tweak the structure again by U1, U3, V3 such that this is 0, this is 0, but now this is 1, this is 0, this is 0, this is 0. This will give me, this is degree of freedom 1, degree of freedom 1, degree of freedom 2, D of number. This is 3, this is 4, this is 5, this is 6. 6 degrees of freedoms are there. So I will call it as the force field corresponding to that, because this is the third degree of freedom. I'll call it as Q3. Even though I'm not computing here, I will call it in that manner. Similarly, for this would give rise to force field of. Now, if I displace with U1 V1, U2 V2, all three 0, but this one 1 and U3 0, V3 0, this would give rise to another set of force field, because this is the fourth degree of freedom which has been unit and all others are 0. This will give rise to some set of forces in the structure which I call it as Q4. Similarly, if I have U1 1 0, U2 0, U3 0, U force 0, U phi. Sorry about that. U1 0, V1 0, U2 0, V2 0, U3 1, and V3 0. Since this is fifth degree of freedom, only fifth degree of freedom is active and all others are 0. So it will give rise to some set of forces which I haven't computed. I'll call it as Q phi. Similarly, U1 0, V1 0, U2 0, V2 0, U3 0, V3 1. This is the sixth degree of freedom. This will give rise to a force field of Q6. So that means I can write something like that. This is a force field due to 1, force field due to 2, force field due to 3, force field due to 4, force field due to the degree of freedom 5, force field due to the degree of freedom 6. When I multiply with U1 V1, U2 V2, U3 V3 will give rise to the global forces, actual global forces, or the actual P1, Q1, P2, Q2, P3, Q3. Okay, so this is nothing but your K matrix. K matrix U is given by Q. So this is my Q, this is my, and this is my K. So what if you look at this K and look at this definition of Q1, Q2, 1 is active and all others are 0, then the corresponding vector corresponding to that given column will represent the forces that keeps the structure under equilibrium for that given degree of freedom. So the Ku is equals to Q or Ku is equals to F, which we derived, this derivation says that this equation is an equilibrium equation. This is only equilibrium when 1 is active. This is only equilibrium when 2 is active. This is only when 3 is active. When 4, because this is first degree of freedom, second degree of freedom, third, fourth, fifth, sixth. But when every degree of freedom to some random value it is active, then the equilibrium forces is by K. And Ku and their acting forces is given by this. So your internal resistance is this, the external forces are that, and hence this equation is the generic equilibrium equation of the structure. So even if you have looked at our previous chapter 2, where we showed that the method of weighted residuals or principle of virtual work or the variational form, whatever we took, we showed that our governing differential equation boils and our governing differential equation is our equilibrium equation. Weak form is also an equilibrium equation. Ku is equals to F is also an equilibrium equation. The only difference is K is equals to F or Ku is equals to Q is a discretized form of the equilibrium equation. So even in here, with more intuitive manner, what we showed that when all are tweaked not by unit distance. Here it is not unit distance anymore. It can be of certain values. When they are there, then these are the unit responses. So this combination will give rise to your these force field of the equilibrium forces. So this is a more physical form of deriving strain curve. So with this as the thing, let me derive what we have done for the inclined beam in the previous session, so that a generic beam can be handled with whatever is the random orientation. Because we had only 3 nodes in this, I could tweak each and everything and I could write it in a better shape. But not always you can have, you can write and everything, then it will take assembling the stiffness matrix in the previous, like that of the previous class. Okay, so for that what I will do is I'll try to consider I'll try to consider the simple uh, inclined bar, but before that let me just narrate few properties of this one. So this one, what we have derived, this K is a global stiffness matrix, and the global stiffness matrix, you cannot solve this as it is, because this has been not constrained to arrest the rigid body motions. To solve this set of equations, what I suggest, or what you need to do, is you should also put the corresponding boundary conditions. Here the boundary conditions in this problem is the third U3 is constrained, because this cannot go along this direction. So here U3 is equals to 0. Now if you come to here, U2 equals to 0 because it cannot move in this direction. At the same time, it cannot move also in that direction. So V2 is equals to 0. So for this given problem, U2 equals to 0, V2 equals to 0, and U3 equals to 0. We substitute this boundary conditions, then the structure is statically stable. And once the structure is statically stable, after you put that one, then only you can get stiffness matrix. Reduced stiffness matrix has to be inverted. Anyway, for the completeness, I didn't give you what is Q3, Q4, Q5, Q6. Let me write the full form of this K in its full glory, because that will complete my problem to the fuller extent. Is given by Q1 first column, Q2 second column, Q3 third column, Q4 fourth column, Q5 fifth column, is nothing but, so we have already obtained the Q1, which is equals to A3 plus 0.36 K2 minus 0.48 K2 minus K3 minus 0.36 K2 plus 0.48 K2 minus 0.48 point K2 0.64 K2. Q3 I haven't derived it, I'm directly giving it, but you can tweak your U3 is equals to 1, and the third degree of freedom is U2 is equals to 1, and then rederive it for yourself, but I'm directly giving you the solution. K3 0 plus K3 0 0, 0. Similarly, for u2, v2 is equals to 0, you will get 0, 0, 0, k1, 0, minus k1. And q5 is given as 0.36, k2 plus 0.48, k2 0, 0 plus 0.36, k2 minus 0.48, k2. And q6 is given by 0.48, k2 minus 0.64, k2 0 minus k1 minus 0.48, k2, this is k1 plus 0.64, k2. So this is corresponding to u1, this is corresponding to when u1 is equals to 1, this is corresponding to when v1 is equals to 1, this is corresponding to u2 is equals to 1, this is corresponding to v2 is equals to 1, this is corresponding to u3 is equals to 1, this is corresponding to v3 is equals to 1. If you look at this, again the properties of k, which we discussed in the previous chapter, you see that this is symmetric matrix and the diagonals are all positive. This is a positive, this is positive, this is positive, this is positive, this is positive, and this is positive, and this column row is same as the first column, this second row is same as second column, third row is same as third, fourth, fifth, and sixth. So the properties what we studied still remain same. So, and anyway, guidelines which we generally write it, why I always write it, you can also write it again with since the columns and rows are same, I can as well as write as these things corresponding to that v2 so I missed it somewhere. This is 0, there is a 0 which I missed it here. So v2 v2 u3 v3. So now this is our K matrix. If you have to solve these things, you know that what are the degrees of freedom, you know that u2 is equals to 0, and let us see here again the degrees of freedom which we already know is u0, v2 0, u3 0. So knock off all the things that corresponding to those rows and columns. So I try to knock it off. This is remove this because they're already 0. Remove this row. Similarly, remove this. Similarly, remove this. Remove this. Then your k uu, which we have learned in the previous class, some of the earlier k3 plus 0.36 K2 minus 0.48 K2 plus 0.48 K2 minus 0.48 K2 0.64 K2 minus 0.64 K2. This is plus 0.48 K2 minus 0.64 K2 and K1 plus 0.64. So if you look at this, this is still symmetric. And the diagonals are positive. But this is okay, but sum of row or column is not 0, whereas in here it is 0 because it is under self-equilibrium, whereas the other one is not. So now you take KUU. So now what you need to solve is KUU times, U1, V1, V3, because these three things are not known, is equals to P1, Q1 and Q3. If you solve for this, then you can solve for the thing. Anyway, let us see what are the forces that are acting on the things. Let's just write what is P1, Q1, P2, Q2, P3, Q3 acting on our structure. So we know that on the given structure, which we have seen here, there are no loads acting in the 3, so there is no P3, Q3, there is no loads acting on this. There is only vertical load acting in the Q direction, in the minus direction. So this value would become 0 minus P 0, 0, 0, 0. So knowing this information, this is external loading. I can write this value here times U1, V1, V3 is equals to 0 minus P 0. Now I know this, I know KUU, which is nothing but this, and I can determine that these three. So my U1, V1, V3 is KUU inverse of 0 minus P0. Anyway, I know my other things, which is U2, V2, U3 are already known to us, which is 0, 0 and 0, because we know these things. So if you invert it, you know all these things. Then you put back into your all these values into this equation. You put all these things, multiply it, the remaining reaction forces will be automatically determined by multiplication of those things. That's how you solve a complete truss problem. This is a better example. And in this example, compared to the previous class, even though we had an inclined members, what we showed primarily is the column vectors or the row vectors of the stiffness matrix is nothing but the equilibrium forces that are required for keeping the corresponding degree of freedom value 1 and all other degree of freedoms equals to 0. So since we have n degrees of freedom, we have to obtain n such vectors of forces, and those vector forces, when you put it as a package in an order, it will give you your global stiffness matrix. However, if you have, let's say, 50 degrees of freedom, going through this method will become very difficult. So this method is only to understand that the K matrix is nothing but an equilibrium conditions or equilibrium forces. But in order to deal with the bigger problems, we need to deal with a template based rather than tweaking each and everything and writing the vector forces. That will take very longer time and it is very tedious in nature. So to deal with it, we'll come up with the same thing, how to deal with the inclined things, just like the transformation which we have studied in the previous class. Okay. So for that, anyway, I'll leave it here for you to invert these things and determine the things. So I will go to the next problem, that is element stiffness. This is the next topic. Before I go to this, let me just check if you have any questions. Let this be node I. We know that the displacement at this node I is ui, ei, and the displacement, that is, this is along x direction, this is along y direction. Similarly, this is uj, vj, this is along x direction, this is along y direction. The corresponding forces acting on these things would be pi, qi, vj, qj. Okay, so now let's do develop the stiffness matrix very similar to what we have developed in the previous class. Let's call this angle, let's call this angle theta. So we can write our length L as, let's say the coordinates of this is xi, yi, xj, yj. The length would be, our length square is equals to xi minus xj whole square plus yi minus j whole square. Okay. So similarly, let's define capital S, which is sine theta. Sine theta is defined as yj minus I divided by L, and cosine theta is equals to xj. The length of the beam is this one. we have done in the previous here. Redraw it again. Unit distance. So then it will go to this place. So let's assume that this angle theta plus d theta are theta dash, and this angle theta. Theta is more or less equals to theta dash. Because our deformations are small, so if this is the unit distance, then I need to again split this thing into two things. One is along the length of the bar, and one is perpendicular to the bar. So this displacement, if I write it along the length of the bar and one perpendicular to the bar, this is c times ui, and this one will become s times ui. So this is ui. The black line is, I'm displacing it by ui, so the red lines is ui and sui. So if this is sui, let's say the stiffness of this element is given by k. We know that k is equals to ae by l of that given element. So in that case, what element f force on that element E will be k times the displacement, which is c times ui. So this is k times c times. Again, if I want to split into a horizontal force and vertical force, can be written as the force acting is Fe is equals to Cui K. Again has to be split into horizontal force, and so let me write it here. This inclined force, which is Cui K, has to be split into Ei Qi Pj Qj. So this is very generic. So you can even substitute for theta is equals to 45, like last time I've shown you, or theta is equals to 90, or theta is equals to any given angle. You can substitute it. The formulation is very generic in nature. And if you look at this thing, this is a single element, planar link element, and with a generic, with any inclination. And as usual, the properties of this is it is symmetric. If you see, if you look at the on the first row is same as the first column, the second row is same as second column, the third row is same as third column, fourth row is same as fourth column. That means this given thing is symmetric, first thing. Second thing is the diagonal is always positive, and if this is not invertible, because it is one single element, and in the single element you haven't constrained the degree of freedom, and hence you cannot invert it. You'll only make use of this thing to assemble it in the global things. And for the global structure, even once after doing the assembly, the global stiffness matrix is still symmetric and unconstrained, so it is also not invertible. Only after substitution of the boundary conditions you will be able to invert the solution. So this is the same thing which we have practiced. So to summarize, let me say what I have done today. We derived K using physical degree of freedom, the amount of equilibrium, and hence the K what we derived today was much more physical than yesterday, where we are just doing it in the assembled form. So that is the first key important thing. Second, using the same concept, we derived element stiffness.